Our next presentation coming up, it's called DHCP Relay Agent Support over Overlay Subnets by Naveen from Nutanix.
Hi everyone, I am Naveen from Nutanix. Today I am going to discuss about a new OVN feature that we are working on to enable DHCP relay support for overlay subnets. Along with me, my colleagues Hujaifa and Mary are also contributing to this feature. Here is the agenda of the talk. A brief introduction about why we want to enable DHCP Relay Agent functionality on OVN. A quick overview on how DHCP Relay Agent works in underlay network. We will use packet flows to discuss about that. How are we implementing DHCP Relay Agent functionality in OVN? DHCP Relay Agent functionality packet flow in OVN. OVSDB schema changes to enable this feature. A simple config example, limitations, references and current status of the feature. Let's talk briefly about why we want OVN to act as DHCP relay agent. IP address management for overlay subnets cannot be done by an external DHCP server because overlay subnets are isolated. They sit behind a logical router and DHCP broadcast messages get suppressed at the logical router. In a typical enterprise deployment where there are multiple subnets spread across multiple locations, IP address management is generally done by centralized DHCP servers. So we want OVN to act as DHCP relay agent. This enables network admins to use same DHCP servers to do IP address management for both underlay and overlay networks. To forward the DHCP request between DHCP clients and DHCP servers, relay agent functionality is generally enabled on the routers, which are acting as a default gateway. Before we dig how we implemented DHCP relay agent functionality in OVN, let's quickly go through how it works in the regular underlay network using packet flow diagrams. In this slide, we are capturing DHCP discover and offer packet flow in a regular underlay network which has DHCP relay agent deployed. As shown in the diagram, there is a DHCP client and router which has relay agent functionality enabled. They both are sitting on the same subnet, and there is a DHCP server sitting on a different subnet. The DHCP client is initiating a discover packet, which is a broadcast. The relay agent sitting in the same broadcast domain receives this packet, processes the packet and converts into an L3 unicast packet and gets forwarded to the DHCP server. If you see the outgoing packet from the relay agent to DHCP server, the destination IP is pointing to DHCP server. Source IP is updated with the outgoing interface of the router. Source port is updated. GI address field in the DHCP header is updated with the internal interface IP of the router on which broadcast packet is received, which is 192.168.1.1. The GI address information is used by the DHCP server to find out from which pool the IP address has to be assigned for this particular request. In this case, it assigns IP from 192.168.1.0/24 subnet. It generates an offer and sends the packet to the relay agent. If you see, the destination IP in the offer packet coming out from the server is pointing to GI address 192.168.1.1. This is how the packet reaches relay agent. Once relay agent receives the offer packet, the packet is processed and then forwarded to the DHCP client. By updating the destination MAC address to the client MAC address, this information is extracted from the DHCP header, and the destination IP can be broadcast or offer IP, which is based on the flag DHCP client is setting on the request packet. The destination port is updated and the GI address is reset. Once DHCP client receives the offer packet, it initiates the DHCP request packet. As shown in the diagram, DHCP request packet is also a broadcast packet. DHCP relay agent sitting in the same broadcast domain processes this packet, converts the packet into the unicast. As we can see, this packet is destined to DHCP server. All the required fields are updated in the packet, like source IP, destination IP, source port, GI address information. Now the DHCP server processes this request packet and responds with a ACK packet, and this packet is destined to 192.168.1.1, which is the GI address. And now this packet is received by DHCP Relay Agent. It processes the ACK packet and it updates the required fields, and then the packet is forwarded to the DHCP client as shown in the diagram. So with this, IP address assignment process is completed. Once IP address is assigned to the DHCP client, all future DHCP renews or DHCP release packets are directly destined to DHCP server. As shown in the diagram, DHCP renew request is destined to DHCP server, and when server is responding it with DHCP ACK, it is also directly destined to the DHCP client. Relay agent is not involved here. Now let's understand how we have implemented DHCP Relay Agent functionality in OVN. To implement DHCP Relay Agent functionality in OVN, we need to replicate all its functionality in the logical pipelines of OVN. We have implemented the Relay Agent functionality in the logical router pipeline. DHCP requests originated from the DHCP client are processed on the source node where DHCP client is deployed, whereas DHCP response packets coming from DHCP server are processed on the node which first receives the packet from the underlay network. Generally, in a multi-node cluster deployment, this is an redirect chassis node. There are some prerequisites to use DHCP Relay Agent feature in OVN. The first one is logical router IP should be assigned statically from the same overlay subnet which is managed by DHCP server. The second one is overlay subnets managed by external DHCP server are expected to be routable directly from the underlay. The third one is LRP IP should be configured as a default gateway for the overlay subnet on the DHCP server. We'll discuss about this in a more detailed way in the next slide. This slide is capturing high-level DHCP request and response flow in OVN logical pipeline when relay agent functionality is enabled. As shown in the diagram, DHCP request flows are represented in purple lines and response flows are represented in green lines. First VM is initiating the DHCP request. The request is coming to logical switch. The logical switch is forwarding the request to logical router. Logical router on the source node converts the packet to unicast and the packet is destined to DHCP server. This packet gets routed to underlay via redirect chassis node. Once server receives the request, it sends the reply. The reply packet lands into the logical router pipeline on the redirect chassis node. The logical router processes the packet and forwards it to the logical switch. The logical switch forwards the packet to the VM. This is how high-level request response flows looks in the OVN logical pipeline. And as noted in the slide, the LRP IP 192.168.1.1 has to be statically assigned from the same overlay subnet that DHCP server is managing. And this subnet is expected to be routable from underlay. The main reason for this is the DHCP response packets coming from the server during IP assignment process, offer and acknowledgement packets are destined to 192.168.1.1. And also once IP address assignment is completed, VM start talking directly to the DHCP server. These are the reasons why this subnet is expected to be directly routable from the underlay. And apart from this 192.168.1.1 IP must be configured as the default gateway for this subnet in the DHCP server configuration, so that VMs present in this subnet talking to any other subnet, the default gateway points to the LRP IP. So all those packets gets routed through the logical router pipeline. This slide captures new pipeline stage and actions introduced to support DHCP Relay Agent functionality in OVN. DHCP request packets are processed in the existing pipeline stage of logical router. To process DHCP response packets, we have added a new stage in the logical router pipeline. There are two new actions added. One to process DHCP request packets, the other to process DHCP response packets. In both cases, the packets are redirected to ovn-controller. the OVN controller do required sanity checks on the packet. It drops the packet if any check fails. Otherwise, the required information is updated in the packet and then it's sent back to OVS. Now let's discuss about detailed logical packet flow in OVN when DHCP Relay Agent functionality is enabled. This diagram is capturing DHCP discover and DHCP offer packet flow in OVN logical pipeline when DHCP Relay Agent functionality is enabled. At step number 1, VM is initiating DHCP discover packet, which is a broadcast packet. Logical switch receives this packet and converts it into L2 unicast packet by setting the destination MAC to LRP MAC. At step number 2, logical router processes this packet. There are required flows installed and the logical router input pipeline stage to process these packets and forward them to the OVN controller. At step number 3, OVN controller receives this packet, do the required sanity checks on the packet. Once the checks are successful, it updates the GI address to LRP IP and send back the packet to OVS at step number 4. And we are using OVS action to update other L3, L4 headers in the packet. The source IP is set to LRP IP, destination IP is set to DHCP server IP, source port is updated. And after this, the packet becomes L3 unicast packet and it gets routed to underlay like any other IP packet. In a multi-node cluster setup, any packet that has to be routed to underlay gets forwarded to redirect chassis node. From there, it enters to the underlay network. At step number 5, the packet enters to the redirect chassis node, and at step number 6, the packet is going to the DHCP server, which is sitting in the underlay network. The DHCP server now processes the packet. It uses GI address information to identify from which pool the IP address has to be allocated. It creates DHCP offer packet. It sends the packet to the LRP IP. Now the redirect chassis node receives this packet. The logical router on the redirect chassis node processes this packet. There are required flows installed to match the packets coming from DHCP server and forwards them to OVN controller. Now OVN controller receives the packet at step number 8. It updates required information in the packet. The destination MAC is set to the VM MAC. This information is abstracted from the DHCP header. The destination IP is set to either broadcast or offer based on the broadcast flag set in the DHCP header by the client. And GI address is reset. And at step number 9, the packet is sent back to OVS. We are using OVS actions to update the source IP address and the destination port in the packet, and the packet is outputted to logical switch at step number 10. Since the destination MAC is already set to VM MAC, at step number 12, the packet enters to the VM. This is how DHCP discover and offer packet flow looks in the OVN logical pipeline. This packet flow diagram captures DHCP request and DHCP ACK packet flow in OVN logical pipeline. This flow is exactly same as DHCP discover and DHCP offer packet flow. As we can see, once DHCP offer is received by the VM at step number 1, it is originating DHCP request, which is a broadcast packet. Logical switch receives this packet, converts the packet into L2 unicast by setting the destination MAC to LRP MAC. At step number 2, logical router receives this packet. There are required flows installed in the logical router input pipeline stage to process these packets and forward them to OVN controller. At step number 3, the packet is received by OVN controller. It do required sanity checks on the packet, and after that it sets the GA address to LRP IP and send back the packet to OVS at step number 4. And after that we are using OVS actions to update other L3 and L4 headers in the packet. The source IP is set to LRP IP, the destination IP is set to DHCP server, and source port is updated. And after this, the packet become like any other L3 unicast packet and it gets routed to underlay. And in a multi-node setup, any packet that has to get routed to underlay, it is forwarded to redirect chassis node, and from there it enters into the underlay network. As we can see in the diagram, at step number 5, the packet is entering the RC node. At step number 6, it is exiting the RC node. Now the DHCP server receives this packet. It processes the packet and generates the DHCP ACK, which is destined to LRP IP. Now the logical router sitting on the RC node process this packet and forwards the packet to the ovn-controller. Now the ovn-controller do the required sanity checks on the packet, and after that it updates the required fields in the packet like destination MAC, destination IP, and GI address is reset, and packet is sent back to OVS at step number 9. And we are using OVS action to update the source IP address and the destination port in the packet. At step number 10, the packet is outputted to logical switch pipeline, and then since the destination MAC is already updated, the logical switch knows to which port the packet has to be forwarded. At step number 12, the packet is forwarded to VM. So this is how the request and ACK flow happens, and after this the IP address assignment process is completed, and any future IP address renew or release messages are directly exchanged from the VM to the DHCP server. The logical router not intercept those packets. This slide captures all the logical flows that are created when DHCP Relay Agent functionality is enabled for one subnet that has one VM port connected. The first flow captures all the DHCP broadcast packets coming out of the VM port, and these packets are converted to L2 unicast. As we can see in the action, the Ethernet destination is set to LRP MAC and output is set to LRP port. The second flow is added in the logical router IP input stage. This flow matches all the DHCP broadcast packets coming on LRP port and forwards these packets to ovn-controller. Along with that, we are using OVS actions to update other L3 and L4 headers. The third flow is added to capture all the packets coming from DHCP server to LRP IP, and we are just deferring these packets to a later stage. We are not doing anything in action other than submitting to the next table. The main reason we are deferring these packets to a later stage is to maintain symmetriness for DHCP request and response packets in the logical router pipeline stages. The last flow is where we are catching these packets and then redirecting to ovn-controller, and along with that we are using OVS actions to update L3 and L4 headers information, and finally the packet is outputted to LRP port. That is when the packet enters into the logical switch pipeline. This slide captures OVS DB schema changes that are done to enable DHCP relay functionality. There are total 3 changes. First one is we have added a new table, DHCP relay. This table stores DHCP server IP address information. Each row stores one server IP. The second one is we have added a new column to logical router port table. This column refers to an entry in the DHCP relay table. The last one is we have added a column to logical switch table. This column refers to an entry in the logical router port table that has a DHCP relay column set. This is the example config to enable DHCP relay agent functionality. The first command is creating a logical switch. The second command is adding a port to it. And the third command, we can notice that logical switch port is configured only with MAC address. Since this subnet is managed by an external DHCP server, IP address is not known. Command number 4 is creating a logical router, and in command number 5, we are creating a logical router port and assigning an IP address and MAC address to it. The logical router port IP is used to update the GI address field in the DHCP packets. Command numbers 6 to 9 are used to attach logical switch and logical router. Command number 10 to 12 are what really enabling the feature. In command number 10, we are creating an entry into the DHCP relay table to store the DHCP server IP. In command number 11, we are updating logical router port to use write DHCP server IP. And in command number 12, we are updating logical switch to use write logical router port that has DHCP relay set. Command number 11 make sure that all the required logical flows are created in the logical router pipeline stages for DHCP relay agent. Command number 12 make sure all the required logical flows are created in the logical switch pipeline for the DHCP relay agent. Here is the limitation if you want to use DHCP relay agent feature. Since all the logical switch ports are configured only with the MAC address, any OVN feature that depends on IP address is not supported on the subnets which has DHCP relay agent enabled. Here are the references that we have used. The current status of the feature is development is in progress. If anyone is interested to see the RFC patch, here is the link. Thank you everyone. Now we are open for questions.
All right, thank you very much. Oh, my screen just dies. Oh, it's back. Thank you very much, Naveen. It brings back some memories of the past. I did a lot of DHCP client server relay agent in the past when I was still working at a router company. So interesting to see all the bits that not much has changed so far. So that's good to see. Let's see if we have any questions on the Q&A. I think we're good. There's nothing there. Let's see. Oh, there is a question here. It's from Hanlu. Is it possible to use the IP of DGP on the redirect chassis as the router IP for the relay server communication? Would this avoid the requirement of the routing overlay subnet in the underlay?
But the challenge is, the GI address field, whatever we are using, right, which we are setting to the LRP IP, that has two significant purposes. One is that is the IP which DHCP server uses to figure out from which pool the IP has to be assigned, and all replies it will send to whatever, irrespective of the source IP field in the IP header, it will always reply to the GI address field which is in the DHCP protocol header. So the IP header, source IP doesn't really matter. So whatever, so this needs to be routable. The subnet has to be the overlay subnet that we are managing, right? That must be routable.
All right, thanks for asking the question. I think Hanzu replied that he understands the answer, so that's even perfect. So I don't have to, think about if it's all right. So thanks a lot. I do not see any other question. Oh, there is another one popping up, so that's good. So this one is from Numan, and he says, if a same logical port VM sends multiple discovers, does it get new IPs for every request?
So from the relay agent point of view, we are forward, we have required flows to forward it. So it's up to DHCP server. So since it's in its cache, so it maintains that MAC to IP binding. So I think so it might reissue the same IP.
Yeah, from what I remember a long time ago is that the DHCP server allocates an IP address and then keeps it in the cache for a while, and then if it's getting out of the cache, it will remove it. So, but yeah, it depends. So I guess the answer is it depends on the DHCP.
It depends. Yeah, correct. If the cache expires, yeah, it might it'll get new IP. Yeah.
All right. All right, so there's a follow-on question from Numan. He says, but the source IP address has changed. The source MAC. He says the source MAC might have changed to the router's port MAC, right?
No, the DHCP server relies on whatever is in the protocol header. So in the protocol header, the client set the MAC, which we are not touching. I mean, the relay agent is not touching. So it's still the client MAC.
Yeah, I hope that answers the question. All right, he says thanks. Okay, so I see no further questions. So Naveen, a lot of thanks for bringing up the memories, and thanks for the talk. And hopefully next year we have another talk. That will be very cool.